Well, let's see what we can say about the power series, the sum of x to the n over 2 to the n. When we expand this sum, it's an infinite sum, and it's 1 plus x over 2 plus x squared over 4 plus x cubed over 8, etc., etc. So again, it's like an infinite polynomial, but we also know that no matter what the value of x is, this is going to be a geometric series. So when x is 0, this power series is 0 to the 0, which we define to be 1 in this case, plus 0, etc., etc., and this converges to 1. And when x equals 1, this power series converges. It's the sum from 0 to infinity of 1 over 2 to the n, and this is a geometric series with r equals 1/2, so it converges to 1 over 1 minus 1/2, which is 2. If we actually take x equals 2, this power series becomes the sum from 0 to infinity of 2 to the n over 2 to the n, which is 1 plus 1 plus 1, etc., etc. And this diverges since it's a geometric series with r actually equal to 1. So what can we say? Well, this series is always a geometric series, no matter what the value of x is. And it's going to converge when the absolute value of r is less than 1. And r in this case is x over 2. So this series will converge when the absolute value of x over 2 is less than 1, and it diverges if the absolute value of x over 2 is greater than or equal to 1. And of course, the absolute value of x over 2 is less than 1. We'd like to translate that to some expression in x. Saying the absolute value of x over 2 is less than 1 is the same as saying that minus 1 is less than x over 2, which is less than 1. And that's really two inequalities rolled into one. And we can multiply both across by 2, and it's the same as saying that minus 2 is less than x, which is less than 2, or the absolute value of x is less than 2. So we can translate that statement to the series converges when the absolute value of x is less than 2 and diverges if the absolute value of x is greater than or equal to 2. This function or this series makes sense only for x values between minus 2 and 2 on that open interval. We call this the interval of convergence of the series. So the interval of convergence of this series is the open interval from minus 2 to 2, and that's the x values where the series converges. So let's look at the partial sums of this power series as a function of x. So as before, the partial sums here are polynomials of x. They're 1 plus x over 2, 1 plus x over 2 plus x squared over 2 squared, 1 plus x over 2 plus x squared over 2 squared, plus x cubed over 2 cubed, etc., etc. And of course the mth partial sum is the sum from 0 to m of x to the n over 2 to the n. So we've created an animation which graphs the polynomial, which is the mth partial sum here, as m increases from 1 to 20. And of course when m is 1, this is a line, it's 1 plus x over 2. When m is 2, it's a quadratic. When m is 3, it's a cubic, etc., etc. And from our algebraic analysis, we know that the y values on the graphs of these polynomials, as m increases, should have limiting values. They should settle down to a limit, whereas the y values outside of that interval on the graphs of these polynomials should have no limit as m increases. And in fact, we can actually write down what that limit should be for x between minus 2 and 2. In fact, we know that the limit of these partial sums for x between minus 2 and 2 should be 1 over 1 minus x over 2. So here we've graphed that function, 1 over 1 minus x over 2 in red. Now, it's actually defined outside the interval from minus 2 to 2. For values of x between minus 2 and 2, the graphs of the polynomial shown in blue here should get closer and closer to the graph of 1 over 1 minus x over 2, shown in red here, as the m increases. Outside of that interval, the graphs of the polynomials shown in blue shouldn't settle down to a limiting value as m increases. So let's run our animation and see what happens to the graphs of the polynomials, which are the partial sums of this power series, as m increases, the highest power of x increases in the polynomial. And you see our prediction is true, that as m increases from 5 to 50, certainly the y values on the graph of the polynomial get closer and closer to the graph of 1 over 1 minus x over 2, whereas outside the interval from minus 2 to 2, the y values on the graphs of the polynomial don't settle.